Hello all. In this lecture, we will be familiarizing ourselves with molecular spectra, specifically rotational spectroscopy. Here I have depicted different regions of the electromagnetic spectra and what all changes radiation belonging to certain frequencies can produce within a molecule. So we will focus our interest onto microwave region, infrared region, and visible UV region or X-ray region of the spectra in order to understand molecular spectroscopy. So you see that microwave radiation is capable of changing the orientation of molecules. Infrared radiation is capable of changing the configuration of molecules, and visible ultraviolet as well as X-rays can produce changes in electron configurations within the molecule. As we will progress with more details about molecular spectra, we will understand more about what we have depicted here in this table. Molecular energy levels too are quantized as in the case of atoms. In the case of atoms, we already know that electrons cannot take a continuous distribution of energies. The energy levels possible for the electron are discrete. So is the case with molecular energy levels. Molecular energy levels too are quantized. Now, when we are talking about molecules, molecules can exhibit rotational motion, vibrational motion, and the energies associated with rotational motion as well as vibrational motion of molecules, they too are quantized as the electronic energy levels. So, for a molecule, if we are looking at what are the possible energy levels, we can say that molecules possess electronic energy levels, vibrational energy levels, and rotational energy levels. And when, say, suppose light in the microwave region is being absorbed by a molecule, what happens? The molecule changes from one rotational energy level to the other. Okay, when radiation is absorbed, it moves from a lower rotational energy state to a higher rotational energy state. Now, radiation in the IR region, if that is being absorbed, then molecule undergoes a transition between vibrational energy levels, and visible ultraviolet as well as X-rays can produce changes in electronic energy levels. And if we are specifically focusing on what is rotational spectroscopy, rotational spectroscopy is also known as microwave spectroscopy because in order to produce transition between rotational energy levels, the radiation that is to be absorbed is microwave radiation. Or the other way around, if a molecule jumps from a higher rotational energy state to a lower rotational energy state, it emits radiation falling in the microwave region of electromagnetic spectrum. Now consider the case of a diatomic molecule, a rigid diatomic molecule. A rigid diatomic molecule means the bond length doesn't change. And suppose you have a molecule like this whose bond length is R0, and the center of mass is somewhere here. You have a diatomic molecule which is being formed from two atoms of different masses M1 and M2, and M1 is the heavier one, so the center of mass will be located slightly closer to M1, and let R0 be R1 plus R2, where R1 is the distance of M1 from the center of mass and R2 is the distance of M2 from the center of mass. Now, by the equation of moments, M1 R1 equal to M2 R2. Now, you have already studied in your mechanics course how to evaluate moment of inertia about C. Moment of inertia is nothing but mass times uh, distance square. Now, distance square means about distance of the object of the mass from the axis of rotation. Suppose you are assuming the molecule is rotating about an axis passing through the center of mass, then I would be m1 r1 square plus m2 r2 square. Okay. Now, from the equation of moments, you can plug in m1 r1 as m2 r2. So, doing that, your equation becomes like this. Instead of m1 r1, you put m2 r2, and here instead of m2 r2, you put m1 r1. And you can take r1 r2 common, and this becomes m1 plus m2. Now, from the equation of moments, and from the first equation that we had written, R0 is R1 plus R2. Using both these relations, you can write R2 as R0 minus R1, isn't it? Now, you get relations for R1 and R2 in terms of R0 by solving this. Okay. And if we replace R1 and R2 with these relations in this equation in 2.7, you get I as m1 m2 by m1 plus m2 r naught square. So you get moment of inertia in terms of bond length. And this is mu r naught square, where mu is called the reduced mass of the system. So effectively, you have obtained moment of inertia in terms of the individual atomic masses and bond length. Now, by solving Schrodinger equation, you can obtain that rotational energy levels are quantized in units of h cross like this, and the expression for energy is given by h square by 8 pi square I times j into j plus 1, where j is called rotational quantum number, which can take values 0, 1, 2, 3, etc. Okay, this is the expression in joules. Now, if you are to express it in terms of centimeter inverse, all you have to do is you divide the equation by hc, and you get an expression like this: h by 8 pi square ic times j into j plus 1, and your energy in joule gets converted into energy in terms of centimeter inverse. This is a quite an useful unit when you are talking in the spectroscopy realm. And if you take all these are constants, right? H is Planck's constant, 8 pi square is a constant, moment of inertia also you can evaluate, that is also a constant, c velocity of light, that is also a constant. So your if you are taking a particular molecule, this moment of inertia will be a constant for that diatomic molecule, isn't it? So for all these terms, you can write it as a constant capital B. So your energy in centimeter inverse becomes B into J plus 1. So if you are plugging in different values for J, when J is 0, what does energy become? It is 0. When J is 1, what happens to your energy? It becomes 2B, right? When J is 2, it becomes 2 into 2 plus 1 times B. So the energy is 6B centimeter inverse. For J is 3, your energy is 12B centimeter inverse, etc. You can try it for yourself. So these are the allowed energy levels of a rigid diatomic molecule expressed in centimeter inverse. and this constant B is called a rotational constant. Now, in order to obtain a spectrum, you need to have transition between these possible energy levels. Suppose a radiation falls such that it gives enough energy for a molecule to jump from the ground state to the first rotational energy level. It has to supply this difference, isn't it? The incoming radiation should be able to supply the difference in energies between these two energy levels. So you can have a transition from the ground state to the first energy state. So is it with other energy levels. So in order to understand the spectrum, you need to understand the difference between the levels that we have obtained just now. Suppose a molecule in the ground state is absorbing radiation and it is raised to J equal to 1 state. Then the energy absorbed would be E J equal to 1 minus E J equal to 0, isn't it? Now, what's the energy corresponding to J equal to 1? It is 2B. And the energy corresponding to J equal to 0, it is 0. So the difference becomes 2B, centimeter inverse. So the incoming radiation should be able to supply this much amount of energy for an absorption to take place. Okay. Now, if you consider the molecule is raised from J equal to 1 state to J equal to 2 state. Now, what would be the energy difference? The energy difference would be the difference in energies of E J equal to 2 and E J equal to 1, which is 6B minus 2B, and that happens to be 4B centimeter inverse. So in general, to raise a molecule from J equal to the state J to J plus 1, how much energy would be required? The energy required would be the upper state energy minus lower state energy. Lower state is the J state, which has an energy B into J plus 1. The upper state is J plus 1. So its energy would be, instead of all J, you plug in J plus 1. So the upper state energy would be B into J plus 1 times J plus 2. Okay. And when you solve this, you get 2B times J plus 1. So this much amount of energy the radiation should be able to supply in order to raise the molecule from a state J to J plus 1. Okay. So you can consider these energy levels. So from 0 to 1, this is the transition. From 1 to 2, this much amount of energy is required. From 2 to 3, this much difference amount of energy is required. And there is a selection rule for these transitions. So you cannot consider transitions from say 0 to 2 or 0 to 3, etc. There is a restriction for the possible transitions. We are not going to discuss how these selection rule are arrived at, but we will just state the selection rule. Selection rule goes like this: J can change only by plus or minus 1, which implies you can have a transition from 0 to 1 or 1 to 0. You can have a transition from 1 to 2 and 2 to 1. But you cannot have a transition from 2 to 0 or 2 to 4. That is not possible by this selection rule. So applying the selection rule, you can see that, and if you put in different values of J here, when J is 0, this is 2B centimeter inverse. When J is 1, this is 4B centimeter inverse. When J is 2, this is 6B centimeter inverse. So in the spectrum, if you are considering all these possible absorptions or emissions, you can see that in the spectrum you obtain line set 2B centimeter inverse, 4B centimeter inverse, 6B centimeter inverse, etc. So these are the allowed transitions possible for a rigid diatomic molecule, and this is the spectrum that we obtained in the case of rotational energy transitions. I hope this is clear to you. Thank you.